Hey, mathletes, sorry I can't be here with you today. I am in physics in the mountains with my physics students. You'll notice we're in the lab because there's freshmen in my math classroom. We, we didn't want to hang out with them, so obviously. We got some quick notes. It's like application, logarithmic growth and decay, and then you'll hit some homework, and then we'll work on your IA next time I see you on Monday. Okay, so put that in the top of your notes. And sorry about my terrible handwriting. I'm writing with the trackpad. But what I'd like you to do is pause me and try to solve this algebraically. I want to know the intersection of these two lines. Next time we meet, we'll learn how to graph them. And so one does this, the other one does that, and we'll find them graphically. But for now, I want to try to find them algebraically. And so what you can do is like where they hit each other. They have, oh, that's terrible. They have common x and y coordinates. So you can set the y's equal to each other and try to solve. You say, I know in that spot where they hit, the y from this one is the y from that one. And then you can set them equal to each other and then try to solve with logarithms.
Hello. What are we doing here?
Logarithms.
Logarithms? There are only 3 scales that I know in science that use logarithms.
And what are those?
Those scales are the pH scale and the decibel scale.
What's that?
Decibel scale and the radioactive decay.
All right.
Keep focused. Right, I'll let you crack on.
All right, so we're equating the y values, and so we'll substitute in the equations for them. So this is 2e to the x plus 1. It's almost like we planned that. And this guy is 7 minus e to the x. All right, so you can cluster or gather all your e to the x's. So maybe add e to the x to both sides, and you'll end up with 3 e to the x over here. And then subtract 1 from each side, and you'll end up with 6 over there. That's nicey nice. But I can't quite take the log of it yet. Let's get that out of there. Can't quite take the log of it yet. We have to divide off a 3. And so you get e to the x equals 2. 6 divided by 3 is 2. And now we can hit it with our logs. So we can call this log base e. Sorry about the slow tracking. Log base e of 2 should give me x. And so therefore x should be log, natural log. Some of you call it ln, natural log of 2. Leave it. It's an exact value, or if you need a decimal for some reason, throw it in your calculator and you get that, I don't know, 0.69, approximately equal to 0.69. Cool? Great. So, hey Vic. So let's try this. We're going to take those sorts of ideas and work with them with growth and decay. And we did this last time we met. We were talking about a grasshopper plague, and we had a nice equation for the amount of land area being affected per time, like as time changes. And this might be something you could think about for your IA, is like modeling a system that you see in nature, maybe like wildfires or bacterial growth. And so this is modeling like grasshoppers, right? So you could take data from anywhere. You could take data from like the statistics on the wildfires in California that keep cropping up, or in Portugal, if you're from Portugal or whatever. And then model it like this, right? Try to figure out an equation. So we're looking at grasshopper plague. I like this. These aren't grasshoppers, but these are ants. This little one's like, so is this a date? This one's like, no, it's a fig. Because they're sitting on a fig, eating the fig, and she thought it was a date, like the fruit, and also the romantic engagement. I don't know. Anyway, we want to know when. So this is like your grandpa's field has 5,000 hectares. How many weeks until it's completely overrun with locusts? Well, we can solve this with logs using this. I know AN is the number of hectares based on the number of weeks that go by, and so I want to know when that value is 5,000. So we can set it up as 5,000 equals 1,000 times 2, but then they mediate it with this 0.2n, 0.2n. that's great. We want to isolate this piece here. Oh, sorry, trackpad. So divide off the 5,000. Divide the 5,000 by the 1,000, and you end up with 5 equals 2 to the 0.2n. That's lovely, but we want to move this up and out. We want to isolate the exponent. So let's take the log base 2 of both sides, or let's turn it into log form. So we'll say log 2 of 5, and that should give me this exponent of 0.2n. You throw log 2 of 5 in your calculator, and I got log base 2 of, log base 2 of 5. I got that. So 2.3. So you end up with this side being 2.32 equals 0.2n. And then you have to divide both sides by 0.2. And you end up with n is 11.6. And this is in weeks. So it said how many weeks until it's completely overrun? Well, 11.6, so 12 weeks. So like the 11th week, it still isn't completely overrun. You have to wait till the 12th week until it's completely overrun. Another way you could do that is look at it graphically and say, all right, I want, here's 4,000, 6,000. If you had a nice graph, you could graph this equation, and you could graph, so that's this guy, right? And you could also graph this as y2, and that would give you a line like that, and you can see where they intersect if this was a calculator question, right? And it looks about right, like that's 11 and a little bit. Or if it's non-calculator, you do it by hand. They'd have to give you this piece you'd have to be able to do in your head, but there you go. All right, one last one. We also use these logs in, aside from science, as Mr. Gilead said. You can use these in investing. I liked this. I thought this was funny. Acting on advice from his stockbroker, Frank, the ever-shrewd businessman, invested heavily in China because the Chinese market is booming right now, but it's a play on words because it means like China, like porcelain objects. All right. Anyway, so Irina invested 5K in an account that pays this much annually. How long for the investment to reach that? Okay. Well, I know that this will be faster if I click. I know that we take our our initial investment, and we multiply by 100%, you get all of your money back or they're robbing you, plus you get 5.2%, that's this part, right, per year that goes by. And I want to know when that turns into 20,000, so that's where this comes from. Cool. So we'd first divide the 5,000 off of each side to isolate the exponent, so that's what happens here, and then they switched sides. So this is 20,000 divided by 5,000, that's the 4. And then this is the leftover stuff there. Switch it into log form. So they used, oh, that's super annoying. I guess they just took the log of both sides. I wouldn't do that. I'm railroading this. That just seems annoying. I would from there take log base, since we have our this would be a calculator page, 1.052 of 4. I want to get 4 out, and n is my value. And so you'd throw that 1.052 of 4 in your calculator, like that. Like 27.3. So n is 27.3, and now interpret. Find how long it will take for her investment to reach 20,000. This is the number of years, so 27.3 to reach a full 20,000. So at 27 years, at 27 years, it hasn't yet reached what she wants, right? And so this is compounded annually, so you have to wait till the next year. So you round up to 28. How do you know which way to round? Context. Context. Neat. Okay. That's it. You guys have enough tools to mess with this. What I'd like you to try is there's this log applications set in your home learning packet. There's another one after this if you get done with this as well. And then next time I meet, we're going to do our last section, which is graphing. So if you get done with both of these application pieces, you can go on to graphing, but I think we'll have plenty to do. Cool. See you soon.